Hello, I'm Professor McCollum. Today we'll be doing chapter 3 in Zumdahl. Chapter 3 in Zumdahl is stoichiometry, chemical quantities. Most of you probably think about this as being chemical reactions and so on. It's the study of quantities of materials consumed and produced in chemical reactions. Now, before we get to chemical reactions, we do have to talk about the basics of chemical quantities. So let's first talk about atoms. We have a problem with counting atoms because they're so small. They're so very small that we really have no concept of how many there are, say, in a spoonful of sugar, how many atoms or molecules are in that amount of sugar, or a piece of metal, how many metallic atoms are in this piece of metal. It's such a huge number that we really have trouble understanding this. And what we really have to do is we have to figure out a way to count these things by weighing. And the first thing I want you to think about here is I don't want you to get too stuck on how much an individual atom weighs. I don't want you to have to memorize this at this point. At this point, I just want you to think about these things are really small. They're extremely difficult, really impossible to weigh on a per atom basis. So we need to be a little smarter about this and figure out a way to do this. And we need to also figure out the average mass of, let's say, a group of atoms or molecules. The way we do this is counting by weighing, and let's illustrate this by counting by weighing some things that we know a little bit more about, right? So here's an example, very simple example. We have a bunch of marbles, and the bag of marbles happens to weigh 394.8 grams. Now, separately, we may know that 10 marbles weigh 37.6 grams. This gives us a way to determine how many marbles are in this bag of marbles. So first, what we have is we have a conversion factor. This is going to be between the mass of marbles and the number of marbles. And you might wonder why we have this 10 marbles is 37.6 grams. We want to weigh a representative number of the marbles to give us some sort of averaging, but we don't want to have to weigh, a bucket of marbles. The more we weigh, the better our averaging is going to be, but there is going to be a sweet spot there. So this was determined that 10 marbles equals 37.60 grams. An equality like this is going to be turned into a conversion factor. The way we get this conversion factor is we divide both sides by the other, forming 1. So in other words, we get 10 marbles divided by 10 marbles on the left-hand side. Well, this obviously equals 1, but on the other side, it equals 37.60 grams per 10 marbles. Now, we do the math, right? There's an actual math here, 37.6 divided by 10, but we're going to leave the units. So we get 3.760 grams per marble. Now, we could also invert this. In other words, I could have divided the right-hand side by the left-hand side instead of the way I did okay? And what I would also get is 1 marble is 37.60 grams. So we need to be able to get used to seeing these conversion factors flipped either way. It's also important to realize that these conversion factors equal 1. So we can insert a conversion factor like this into any mathematical equation we want, and it does not change anything. All it's going to do is switch between units. I discussed this a little bit in chapter 2. Okay, so how many marbles are in a bag of marbles that weighs 394.80 grams? The way we do this is we write down the information we have, 394.80 grams of marbles, right? It's kind of important to put down what we have. Then we're going to multiply by 1, in other words, our conversion factor. What we want to do now is we want to put the units down to cancel the units of marbles. I'm sorry, to cancel the grams of marbles and introduce number of marbles, right? So we want to put grams on the bottom and marbles on the top. And I have to tell you that if I don't put the unit down first when I'm doing a conversion or dimensional analysis, I invariably do it backwards, right? So I'm going to cancel these grams and I'm going to keep the number of marbles, right? And the conversion we're going to use is this second one, right? In fact, what I could do is I could just copy this and I could paste it down here if I wanted to, right? That looks a little messy though. Maybe I'll plan ahead and do that next time. 1 marble is 37.60 grams. Now, when you do the math, remember that grams cancels and we get 105 marbles. Now, what we have here is you might be wondering about significant figures. We've talked about significant figures in chapter 2 and other lectures. Here we have 5 sig figs and here we have 4 sig figs. So shouldn't this answer be 4 sig figs? Well, yes, technically it should be 4 sig figs, but we want to think a little bit about common sense. We have a integer number of marbles in this bag, right? In other words, there's not a piece of a marble in this bag. Somebody put a specific integer number of marbles in this bag. And since the answer needs to be an integer, we need to think a little bit and say that our answer actually has 3 sig figs and it's an integer. This is a little bit, this might be a little bit foggy to you, but common sense should prevail sometimes. Okay, well, in everyday life, we weigh things all the time to figure out how many there are, right? We pay for cherries or other produce at the grocery store by weighing. We might get a box of nails that weighs a certain amount, and we need to figure out some sort of conversion to know how many nails we need to use to do a job, and so on, right? So we count by weighing all the time. Recipes, another example where we count by weighing. So maybe it'll help for you to think about that, all the ways in everyday life that we use counting by weighing. Now, let's now talk about atomic masses. In other words, the masses of atoms. And then we're going to naturally build this up to collections of atoms, in other words, molecules. But let's start with just atoms. Atomic masses. Well, we don't really need to attach a specific unit to atomic masses if we don't want to. So what we're going to do is we're going to use a relative mass. We're going to call 1U equals 1 relative mass unit. So this is going to be the mass unit we're going to use for atoms. And all we know at this point is that 1U is about the mass of an atom, right? More or less. In the same way that a kilogram is about the mass of a textbook, right? Your textbook might be more, might be less, but it's about a kilogram. And that's all we want to define about this mass unit at this point. We don't really want to get too specific. And this is a little bit hard, but it's just this kind of generic mass unit. We must define this though, right? So what does 1U represent? Exactly. Well, we want to use an element, an atom of a specific element, to define an atomic mass unit, a U. Now, you may know from past experience that hydrogen weighs about 1, right? Hydrogen consists of a proton and an electron, and as we've seen, protons are much more massive than electrons. We typically ignore them. And we've learned earlier that the relative mass of a proton is 1, the relative mass of a neutron is 1, and relative mass of an electron is very small. So you may think, this is great. Let's use the mass of hydrogen 1 atom to do this. Well, there's a problem with this, right? First off, write this down, problem. The natural form of hydrogen is H2 in the gaseous form. This is actually two problems. The first problem is hydrogen atoms are not a naturally occurring thing, right? So we'd have to do something like break apart hydrogen molecule to get hydrogen atoms. The second thing is hydrogen is naturally occurring gas, and gases are not very convenient to weigh. They keep flying off the balance when you put them on the pan and so on. So this turns out to be not a good choice, right? Now, it turns out that over the years, many different things were considered and tried to define the mass, the atomic mass unit. But what was finally settled on is carbon-12. Carbon-12, carbon, right? All you have to do to get carbon is burn an organic substance and you have the ash, which is carbon, right? And we're going to use a specific isotope of carbon, carbon-12, right? As we're going to see that naturally occurring carbon is a mixture of isotopes. But this really doesn't matter because in a sense, defining the atomic mass unit is a thought experiment, right? So what we're going to do is we're going to define 1U is defined as, that's the triple equals, is defined as 1/12 the mass of a carbon-12 atom. This is our definition. There's another reason other than the fact that carbon is very easy to acquire. Carbon-12 specifically has 6 protons, 6 neutrons, and 6 electrons. So there's some sort of averaging out over these different species, right? That might be more just kind of an attractive thing than anything specific. Now, what if you look at the periodic table and you'll see the periodic table looks something like this. This 12.011 is actually the mass of carbon, but what it is the average mass of a carbon atom, okay, in U. Notice there's no units on the periodic table too. This will be important in a little while. So the naturally occurring carbon, in other words, in nature, is a mixture of carbon 12, carbon 13, and carbon 14 isotopes. So, in other words, if we have a handful of carbon atoms, it's going to consist of these different isotopes. The average mass, the apparent mass of a carbon atom is going to be the average of this, right? So this 12.011 U will be the average or apparent mass of a carbon atom, right? No single atom of carbon weighs 12.011 U. It's the apparent mass. Well, how does this work? Well, the mass of carbon in nature is going to be the fraction of carbon 12 times the mass of carbon 12, which we know, we define this, right? The mass of a carbon 12 atom is exactly 12 U because of the way we define the U. But there's other things too. There's the fraction of carbon 13 times the mass of carbon 13 plus the fractional amount or fraction of carbon 14 times the mass of carbon 14. Now, one of the things that chemists do a lot, because chemists use math all the time, right? This is not a math class. I say this all the time. It's not a math class, but math is a very important tool in chemistry. So let's write an equation for this, right? The mass of carbon, the average mass of carbon is going to be the fraction of carbon 12 times the mass of carbon 12 plus the fraction of carbon 13 times the mass of carbon 13 plus the fraction of carbon 14 plus the mass of carbon 14. And now you're thinking, now I have an equation, but I have 6 unknowns, so I can't solve this. But we have some things to help us. We have the sum of the fractions equaling 1. In other words, we would say 1 equals the fraction of 12 plus the fraction of 13 plus the fraction of 14. In this particular case, it doesn't really help us a whole lot because this one equation allows us to solve one of our 3 variables, but we still have a bunch of variables. And let's assume that we know the masses too. We're still going to have a problem with this. Well, what you can do is you can look up on the internet, you can look up table of isotopic masses or natural abundances, right? And what you will find is that the percent of carbon 12 in nature is 98.89%. Well, I mentioned fractions. What's the fraction? A fraction is just turning a percent into a number that's a decimal, right? So the percent divided by 100 equals the fraction. So the fraction of carbon 12 is going to be 0.9889, right? What we'll also find out from such a table that I just mentioned is the fraction of carbon 13 is 0.0111. Now, if you put these things together, you get 100. And what this really means is that the fraction of carbon 14 is so close to 0% or 0 that we're not even going to consider it. Okay. Now, what we can do now is we can use this information to find the atomic mass of an isotope of carbon-13. Let's look and see what we have so far. The average mass of carbon, which is 12.011 U, right? We know this from the periodic table. This equals the fraction of carbon-12 times the mass of carbon-12 plus the fraction of carbon-13 times the mass of carbon-13. And remember, what we're doing is we're ignoring carbon-14. All right, so let's put in some of the numbers that we have. We know that the fraction, right? The fraction of carbon-12 is 0.9889. And we know the mass of carbon-12 is exactly 12 U. We know the fraction of carbon-13 is 0.0111, but we don't know the mass of carbon-13. So this allows us to solve for the mass of carbon-13. And what we're going to find is the mass of carbon-13 is 13.0034 U. Now, it turns out that you can, experimentalists really, not you, but experimentalists can determine the mass of these isotopes to 4 or 5 decimal places in a relative sense. Now remember, this atomic mass unit is, I also referred to it as a relative mass unit. What does this mean? Well, it's because of the way that we determine this. In a little while, we're going to use, or we're going to see how a mass spectrometer works, which is the way experimentalists determine atomic masses and molecular masses. Molecular mass is the corresponding mass of a molecule in U. Just catching up with the slides here, right? So again, it's important to realize that if we went out in nature and plucked one atom of carbon from nature, it would not weigh 12.011 U, right? This is the average mass. Just like on the exam that we're going to have not too far in the future, the average exam score, probably no student is going to have the average exam score, right? Because it's going to be something like 75.015%. But I only give full points. So no student is going to be able to get that score, but it's representative in the same way that 12.011 U is representative of carbon's mass. All right. So as I mentioned, we use a mass spectrometer to determine these atomic masses. How does a mass spectrometer work? Well, it's actually pretty simple. In other words, you're going to be able to understand this, hopefully, in just a minute or two. So let's go over to this slide. You take a sample. So let's imagine a sample of naturally occurring carbon, okay? And you vaporize it, so you turn it into a gas. So then you send it in through this end of the instrument. The first thing you do is you ionize these atoms. So what that means is you're going to kick off an electron. So what you end up with is, say, these atoms that are positively charged, still gaseous, right? Now, charge and mass are the way we do things experimentally on very, very small things. Once these things are charged, we can use an electric field to accelerate them, right? We don't have teeny tiny little guns to shoot atomic bullets, but we can use an electric field to accelerate charged things. So that sends these things on their way. The next thing is a magnetic field that we send perpendicular to the way these things fly. And a magnetic field is going to affect their masses, and it's going to start to split them up according to their mass, right? The heavier things are going to be bent less. The lighter things are going to be bent more, and they're going to hit this detector in different areas. And over time, these impacts on the detector build up little peaks, and you end up with things that look like this. And the height is proportional to the amount, or what we call this is the natural abundance. Okay. Well, you have to do a couple things here. You have to set a 0 point. So in other words, you might send through this mass spectrometer only carbon-12 atoms. There are ways of purifying this, right? So I can send through only carbon-12 atoms. So if you do that, you just get one signal, right? And you can say this is due to carbon-12. So I can come back up here to my sample signal and say that's carbon-12, okay? And then the second thing we can do is we can use the position to determine the mass. And the way this works is you take the distance this way and the distance this way, right? So let's call this L1 and L2. So L2 over L1 is the same as the mass of 2 to the mass of 1. Let's say that the mass of 2 is going to be the mass of carbon-13. Whoops. And we're going to find, you can find this by measuring with a ruler, but most instruments will tell you this. The ratio of these masses is 1.084, right? This means that 1.084 equals the carbon-13 mass over the carbon-12 mass, was exactly 12. And now if you solve for this carbon-13 mass, 1.084 times 12 equals 13.003355 U, which is the same answer we got before solving it kind of mathematically using the average atomic mass. But if you think about it, the average atomic mass is something that we need to solve for rather than the other way around. So this is actually the way that we figure out atomic masses in mass spectrometers, and this is why it's called a relative mass. Notice we still haven't defined what this mass is in terms of things we know, like ounces or pounds or grams or kilograms or whatever. That's a relative mass, right? We're defining it conveniently, and we'll see how this works in scaling up shortly. Okay, here's another problem. Okay, an element consists of 62.6% of an isotope. Okay, so we're going to say the fraction. Let's try to solve this problem over here. The fraction, let's call it 1, is going to be 0.6260, right? I hope you can see that. I just took the percent divided by 100. The mass of 1 is going to be 186.956 U. The fraction of 2 is going to be 0.3740. And the mass of 2 is going to be 184.953 U. So the average atomic mass is going to be the fraction of the first isotope times the mass of the first isotope plus the fraction of the second isotope times the mass of the second isotope. Let's see, I think we have it solved here. And this turns out to be 186.2 U. And if you look on the periodic table for that mass, you'll find out it's rhenium, Re, right? In other words, here's how we do it. 0.6260, the fraction times the mass, 186.956 U, plus 0.3740 times 184.953 U. This equals 186.2 U. Let's do a sig fig check here, okay? Is this number of sig figs correct? Well, these fractions have 4 sig figs. These masses have 6 sig figs. And so it turns out that we're allowed to keep 4 sig figs, okay? The 4 sig figs comes from the multiplication. That gives us 1 decimal point when we do it, right? We add them down, and that's the way it works out. Let's do one more example of isotopic mass. My favorite example of isotopic mass is bromine. Bromine, the periodic table mass, in other words, the naturally occurring mass, or the average atomic mass, is 79.9 U, right? Most periodic tables give you a little bit more decimal places, but I'm just going to leave it 1 for now. Well, it turns out that naturally occurring bromine is 51% bromine 79, and it's 40, actually, hold on. .9 U. Well, bromine is made up of 2 isotopes, bromine 79 and bromine 81. Now it turns out that the mass number is 79 and the mass number is 81. Now remember, A, which is the mass number, is not the same thing as the mass, but they're usually pretty close, right? So the mass of bromine 79 is about 79 U, plus or minus a little bit, and the mass of bromine 81 is about 81 U. All right, well, look at the average mass. What is the natural abundance of each isotope of bromine? We have, let's do this on a number line. It's kind of easy to see on a number line, right? We have 79 over here. We have 81 over here. And of course we have 80 right in the middle. So if one isotope weighs this much and the other isotope weighs this much, and the average mass is just to the left of 80, 79.9, I hope you can see this is about 50-50, right? It's pretty close to 50-50. It turns out that the natural abundance of 79 bromine is 51%, and the natural abundance of 81 bromine is 49%. And this makes sense if you think about it, right? The average is skewed a little bit to the lighter weight. So that means there's a little bit more of the lighter isotope than the heavier isotope. All right, let's move on. Let's talk about the mole or the mole concept. you probably know what the mole is. Avogadro's number is another name for it, Na. Let me just say that there's actually nothing remarkable about Avogadro's number, except for the fact that it exists. I guess I'm really not part of the cult of Avogadro that makes this number into some special big deal. It is an important number, but the number could be anything, right? It just happens to be a specific value. You'll notice I haven't even mentioned what the number is yet. Okay, so it turns out that, again, let me look at our representative periodic table element. We have carbon 12.011. And remember what we said. Let me bring up my periodic table here. This number in the periodic table, here's carbon right here. That's the average atomic mass of a representative carbon atom. Well, the way we use this day in, day out is really in grams, right? But as I said before, notice there's no units attached to the numbers in this periodic table. That's because of the clever choice of scaling up. So we need some scale up factor so we can use everyday masses. Let's say common lab masses. And that common mass is going to be grams, right? Let's weigh out grams of stuff. Okay, so here's how Avogadro's number is defined. Avogadro's number is defined as the number of carbon-12 atoms in 12.0000 grams exactly of carbon-12. Well, so what this means, this is kind of a clever definition, because now what we can say is I can come back to my periodic table mass and I can say, well, that 12.011 is the mass of carbon in U and the mass of Avogadro's number of Avogadro's number of carbon atoms in grams, right? So this gives us a scale-up factor. What is Avogadro's number? It happens to be 6.022 times 10 to the 23, right? What's the unit? It turns out the unit is per mole, right? Okay. Now, the homework problems that you're going to do, and I'm going to give you, and that will be on your first test, do a lot of conversions between number of atoms and moles, and they use Avogadro's number quite a bit. But I have to tell you, the main reason for this is to get you used to and comfortable with the math and dimensional analysis. Most of the time, we do not use Avogadro's number day in and day out in chemistry. What would be the point, right? Why would we define this larger unit of a mole if it wasn't the most convenient thing in day-to-day use? But for now, we are going to practice using Avogadro's number in calculations quite a bit. So let's do an example. An example is here on the slide. Calculate the number of iron atoms in 4.48 moles of iron. So what we're going to do is we're going to write down what we're given, 4.48 moles of iron. Remember, you should always write down the identity of whatever you're working with as one of your units, in this case, Fe. 4.48 moles of iron. Now, I'm going to do what I told you I have to do. I have to put the unit down first, mole, and atoms is going to be on top, right? Look at the unit. Remember, the unit of Avogadro's number is per mole. So the mole's on the bottom. 6.022 times 10 to the 23 atoms in 1 mole, right? When I multiply this out, I'm going to get 2.70 times 10 to the 24 atoms of iron. Now let's do sig fig check. 3 sig figs here. This, well, we have to talk about this a little bit, right? This looks like 4. It's actually not 4. But let's talk about the sig figs and the answers. 3 sig figs in our moles of iron and more than 3 sig figs in Avogadro's number means that we get 3 sig figs in our answer and we're good. But let's talk about this. 6.022 times 10 to the 24 per mole is considered exact. Remember what that means. That means infinitely significant. So what this means in practice is that Avogadro's number does not limit the number of significant figures in our answer when we use it. This is considered an exact number like pi or the gravitational constant, right? And however we use it, it's considered to be exact. I will also say typically in masses, atomic masses, molar masses, and so on, 2 decimal places are kept. Even though we could keep more if we wanted to, I'd say 2 decimal places in masses is something that's very commonly kept. Okay. Now, what's the difference between molar mass and atomic mass? Well, molar mass is talking about moles. Atomic mass is going to be used. So molar mass is typically going to be in grams. Atomic mass is the mass of an atom in U, right? This also applies to molecules too. For molecules, we have molecular mass. So molecular mass strictly refers to the mass of a molecule, individual molecule in U. It could also be formula mass for ionic compounds, right? So molar mass usually refers to more than one thing, common practice. It's not strictly true, but that's what everybody does, right? Okay, so whether you're dealing with molecular mass, let's talk about molecular mass first. The molecular mass equals the sum of the atomic masses. Of the atoms, right? All right, so 1 H2O equals 1.008 U for the hydrogen, plus another 1.0008 U for the second hydrogen, plus 15.9994 U for the oxygen. So the sum is 18.02 U per molecule. The molar mass of water, this is the mass of Avogadro's number of molecules, right? We do this the same way, except we just change the unit. 1.008 grams for the hydrogen plus 1.008 grams for the second hydrogen plus 15.9994 grams for the oxygen, and we get 18.02 grams per mole. Notice the difference in units, right? U, grams per mole. Grams per mole deals with Avogadro's number of things. Now here we have the molar mass of barium nitrate. Barium nitrate is a salt. Right? This is an ionic compound. We cannot isolate a single barium nitrate molecule. So this is actually kind of incorrect saying the molar mass. This is the way we use it, and people say it all the time. But we would actually say the formula weight of barium nitrate is 261.35 grams per mole. In all day-to-day life in chemistry, formula weight, molar mass, same thing. We use it the same way, but what we have to do is we have to realize that we cannot isolate individual molecules of a ionic compound. Talked about this in chapter 2 also. Well, how big is a U compared to grams or vice versa, right? So let's think about how to figure this out. This is a number that I don't really think you should memorize, but you can figure it out quickly. If you can memorize it, that's great. But one of the things I found out about myself is it's really hard for me to memorize facts and numbers. I have to remember them some other way, or maybe calculate them some way. So let's think about this, right? What do we know? We know that for carbon 12.000 grams of carbon equals 1 mole. This also equals 6.022 times 10 to the 23 carbon atoms, right? So basically what we have to do, if we want to know the mass of one carbon atom, this is going to be 12 grams divided by Avogadro's number, or 6.022 times 10 to the 23, right? So if we take a second and punch that in, 12, 6.022 exponent 23 divide. This is 1.993 times 10 to the minus 23 grams per carbon 12 atom. All right, so you can see that this is in the neighborhood of the thing we just got here, right? The number over here on the left in the slide is actually almost 10 times that, but that gives a typical mass of an atom in terms of grams. But this is not the same thing as what 1 U is, right? Let's take this a little bit further. Because this 1.993 times 10 to the minus 23 grams actually equals 12 U, right? That's the mass of a carbon 12 atom. So if we divide this number by 12, then we get 1.993 exponent 23 change enter 12 divide 1.66 times 10 to the minus 24 grams. This is the conversion between grams and U. If you want to memorize this, you can. But it turns out that for me, it's easier to do the calculation. If you can memorize it, then you're doing a whole lot better than me. Let's think about relative sizes of molar masses now, right? For a bunch of different substances, as the molar mass of a compound goes up, the number of moles per 100 grams is going to go down, right? Well, I don't have to pick 100 grams. 100 grams is convenient, but this could be for any fixed amount. It could be a kilogram or a pound or whatever. So for any fixed amount, as the molar mass goes up, the amount contained in that fixed amount goes down. Let's look at an example. If we have 100 grams of two substances, one is 10 grams per mole and one's 100 grams per mole. Well, obviously, the substance that weighs 100 grams per mole for a molar mass has 1 mole. The substance that's only 10 grams per mole has 10 moles. So the smaller molar mass contains more moles per fixed amount. The larger molar mass contains less moles per fixed amount. Sometimes it's the recognize of the fact that we have a fixed amount that's difficult, right? So let's explore this concept with a few slides. First, calculate the number of copper atoms in 63.55 grams sample of copper. Well, from the periodic table, we can see the molar mass is 63.55 grams per mole for copper. So this equals 1 mole, or Avogadro's number, right? Another conceptual question. Which of the following 100 gram samples, fixed amount for each of these, right, contains the greatest number of atoms? Well, magnesium, zinc, and silver. Let's look at our periodic table. Let me find it here. Here's our periodic table. And we find the molar mass, and let's write down the molar masses. The molar mass of magnesium over there on the left is 24.3. The molar mass of zinc, which is in the top middle, is 65.38. And the molar mass of silver is 107 or so. These are the approximate molar masses. Remember, as the molar mass goes up, the amount per fixed amount goes down. So magnesium is going to have the greatest number of atoms, right? 100 grams of magnesium is pretty close to 4 moles, a little bit more than 4 moles. But 100 grams of zinc is about 1.5 moles, and 100 grams of silver is not quite a mole, right? This is about 4 moles. This is about 1.5 moles. And this is about 1 mole, right? I want you to realize that when we're talking about amounts, we don't have to put it in terms of Avogadro's number. You can just use moles and fractions or decimals of moles too. For a lot of people, that's easier than dealing with that 10 to the 23 thing. That's an Avogadro's number. All right, rank the following according to the number of atoms, least to great. As I just said, I want you to realize that number of atoms is proportional to moles, which is proportional to Avogadro's number. So moles is usually the easiest stand-in for amount, right? All right, 107.9 grams of silver. This is 1 mole of silver. 70 grams of zinc. This is a little bit more than 1 mole, right? 63.5, I think, is the molar mass of zinc. And remember, the molar mass of magnesium is 24.3. So this is less than 1 mole of magnesium. Well, 1 mole, a little bit more than a mole, a little bit less than a mole. So zinc is the answer. To do this question, to answer this question properly, we did not actually have to use our calculator, right? Many times you do not have to use your calculator. It's a good practice or test of concepts if you can do that. So the order is B, A, C. All right. Now here's a little bit different question. We might have to look at proportions. In other words, for molecules, remember the subscripts, right? In other words, the amounts. Consider separate 100 gram samples of each of the following. Well, in order to, we want to rank them from greatest to least number of oxygens. The first thing I want to do is I want to write down the molar mass, right? The molar mass of water is about 18 grams per mole. The molar mass of N2O is 44 grams per mole. The molar mass of C3H6O is 58 grams per mole. And the molar mass of CO2 is also 44 grams per mole. And just so you're not confused, let me say that I've calculated these separately, so I had them handy for this problem, right? We also have different amounts of oxygen, right? Water has 1 oxygen per molecule, or 1 mole of oxygen per mole of water. N2O has 1 oxygen. C3H6O has 1 oxygen, but CO2 has 2 oxygen. So somehow we have to take that into account. Let's see how we would figure this out. And I'm going to use dimensional analysis for this, okay? Okay. First, the water. 100 grams of water. The first thing we want to do is we want to figure out how many moles of water that is, right? Grams, moles, 1 mole is 18 grams. Now, typically, I must say that typically if you're going to do a real calculation, you would put down a couple decimal places here. So maybe 18.02. For this problem, no decimal place is going to be enough to answer the question. Okay, now let's look at our dimensional analysis. Grams of water, grams. We're going to convert grams of water to moles of water, but we want to know about oxygen atoms. So I need to convert to oxygens. There's 1 oxygen atom for 1 water, right? Or 1 mole of oxygen atoms per mole of water. All right, so this is a little more than 5. I'm doing this math in my head. 100 divided by 18 is a little more than 5 because 100 divided by 20 is 5, right? So this is a little bit more than 5 moles of oxygen atoms. I think many students would think this was some sort of trick, right? Students call these kind of things tricks, but it's really just experience. So what I'm trying to do in many of these calculations I lead you through, it's ways to get the answer without going to your calculator or without using too much mental horsepower. Okay, I want to lead you to the answer as quickly as possible because this will help you on things like multiple choice tests. All right, let's look at N2O. 100 grams of N2O. 1 mole of N2O, I said, was 44 grams. And once again, there's 1 oxygen per 1 N2O, right? When I do this math, you can see this is pretty close to 2. This is a little bit more than 2 moles of oxygen atoms. I'm hoping that doing this quick and dirty is going to give us enough information. 100 grams of C3H6O, 2. Now, I think I made a little bit of a mistake. I forgot this 2. So let me go back up and correct this because it's going to mess me up. I'm going to get the wrong answer. 2, 2. All right. Remember I said the molar mass was 58. 1 mole is 58 grams. And there's 2 moles of oxygen atoms of 1 mole C3H6O2. Well, this is a little less than 2. 100 divided by 58 times 2. This is probably worth writing down exactly the answer, right? 100. This is 3.44. Okay. All right, finally we have CO2. 100 grams of CO2, 1 mole, 44 grams of CO2, and there's 2 moles of oxygen atoms in 1 mole CO2, right? All right. This is going to be a little more than 4, right? It's going to be 100. I'm going to do this exactly. 44 divide 2 times. This is 4.5. All right. So the ranking 4, 3.4, a little more than 5, a little more than 2. So water wins, right? H2O has more than CO2, which has more than the hydrocarbon C3H6O2, which is more than N2O. So that should be the ranking. Good. It's always nice to see that we've done it right. Okay, let's take a second and think about how we're going to solve problems using dimensional analysis. The first thing might be the hardest part, right? Read the problem and decide on the goal. What is the problem asking for? Many times this is going to be obvious, or you're going to be able to figure out what they're asking for. Sometimes not so much, right? So this might be the hardest single part of solving a problem. How do we get there? Well, if you know what the answer is going to be, say in units, maybe you can work backwards and stack the units using dimensional analysis to work back to where you start with. Now, the last thing, this is very important. I think it's something students often overlook. Does my answer make sense? Is it reasonable? Let me go back a few slides, right? An example of this is on this slide that asks for the average mass of 1 atom of copper. And remember, I took a second and thought about this. 1 atom of copper. It's going to be, the natural way to express this is going to be in U. It's going to be maybe 60 U. There's only grams here. Well, if I'm going to express the answer in grams, the answer is going to be tiny, right? It's going to be a really, really small number, something times 10 to the minus something. And that way we could see that E had to be the answer, right? It's the only reasonable answer. So one of the things I say to students often is you need to know what your answer is, more or less, before you solve the problem, right? And what I mean by that is in ballpark terms. You need to know whether your answer, a reasonable answer, is 10, or is it 10 to the minus 15, or is it 10 to the 10, right? You need to know the size of your answer and if it's reasonable. Okay. The next thing we're going to talk about is chemical composition. Or what's in that stuff. How do we determine what our stuff is composed of and what amounts? That's chemical composition. All right. As an introduction to chemical composition, let's think about a very common chemical composition that we see in stores and hardware stores and other things. And that's mass percent. Composition expressed in mass percent is common because it's easy to understand for non-scientists, right? It's basically parts out of 100. So if you're comparing fertilizers and you want some magnesium in your fertilizer for, say, your pepper plants, and you know that you need at least 15% by mass magnesium in the fertilizer, then that's easy to imagine, right? If you put 100 grams of fertilizer down, you're putting 15 grams of magnesium, and so on. So our first example of chemical composition is going to be percent by mass. Percent by mass is defined as the mass of, let's say, the element divided by the total mass of the sample times 100. If the sample is a pure substance like ammonium nitrate, then you can figure out the mass of the nitrogen and then convert to percent by mass. Right. Typically, the way you do this is you can use any fixed amount, right? The law of constant composition says for a pure substance, the composition is constant no matter how much of it that you take, right? We're going to use this to our advantage shortly when we talk about empirical formulas, right? So we have some fixed amount, and usually the fixed amount we take is a mole. Right, so we'll just take a mole of our compound to figure out the mass percent. Well, remember this hydrocarbon we just worked with, C3H6O2. Let's figure out the mass percent carbon in this compound, right? All right, well, what's the molar mass? Let's figure this out in a little bit more detail than we did last time. I just said about 58, right? This is going to be 3 times 12.01 grams per mole, 6 times 1.008 grams per mole, and 2 times 15.9994 grams per mole. So the molar mass of this is the molar mass is 78.62 grams per mole. That doesn't seem right to me. So I'm going to do it again. It is, in fact, 74.07 grams per mole, right? So what we're going to do is we're going to figure out the mass of the carbon over 74.07 grams times 100. The mass of the carbon is just the 3 times 12.01 grams. And this is 48.06% carbon by mass. Now we could use this as a conversion factor, right? .06 grams of carbon and 100 grams C3H6O2. So this form may be convenient for you to use in other problems. Right. Here we have another example on the slide of iron oxide, right? When you do these percent by mass calculations, you're always going to have to figure out the molar mass of the compound itself, 2 irons, 3 oxygens. That goes in the denominator. This should be a multiplication, not an n. And here we see that the mass percent of iron and iron oxide, iron 3 oxide, is pretty much 70%. Okay. Let's do this problem. We did a very similar problem that's using these compounds before, right? But what I want you to realize is even if you're asked to rank something according to percent by mass, you may not have to do a full percent mass problem. You may be able to just look at the fraction and decide, right? So let's do an example here. We're going to rank these compounds from highest to lowest percent oxygen by mass. For water, the percent by mass, well, first of all, the molar mass is 18 grams in 1 mole. How many oxygens are in water? 1 oxygen per water. That's 16 grams times 100. Let's not even do the math. Let's just look at these expressions and see if we can figure it out. For N2O, you'll remember that the molar mass was 44 grams. There's 1 oxygen in N2O, so this is going to be 16 grams. Well, you can see that the water percent by mass oxygen is much higher than the N2O. Remember that this was, for the hydrocarbon, it was 74 grams. There's 2 oxygens, and that's 32. We can see this is pretty close to 50%. And the CO2, remember the molar mass of CO2 is 44, 32 grams. So to me, without doing this math, it looks like this is the heaviest. This is next. This is 3, and this is 4. We just have to rank them. We don't necessarily have to get the exact answer. H2O, CO2, the hydrocarbon, and N2O. Okay. Okay. Now, there's a problem with percent by mass. If you think about it, and we're dealing with chemical composition, we want that chemical composition to be unique. In other words, we don't want to have the same form of the chemical composition represent 2 different elements. And that's, I'm sorry, 2 different compounds. And that's exactly what can happen with percent by mass. Percent by mass is not necessarily unique for different compounds. And this brings us into the idea of empirical formulas. Let me give you an example. The formula for a simple sugar C6H12O6, right? And the formula for formaldehyde used to be used as an embalming fluid, but it's a carcinogen, so we don't use that anymore. CH2O. These are individual molecules, right? Formaldehyde is a small molecule and the sugar is a larger molecule. But what we find out that if we figure out the percent carbon by mass of each of these compounds, right? For the sugar, it's 6 times 12.01 divided by 180 grams per mole. That's the molar mass of that sugar, times 100. This is the same. I'm just going to leave it like that, okay? The formaldehyde, it's just a single carbon, and the molar mass is 30 grams per mole, right? Well, a number of different ways you can figure this out, right? Let's look at the sugar. 6 times 12.01 divided by 6 times 30, that's another way to write 180. You can see the 6's cancel, and this is the same as 12.01 divided by 30, which is the formaldehyde. So without even figuring out what exactly the percent by mass is, 12 over 30, we can see that the percent by masses of carbon in these two compounds is the same. In fact, the percent by mass of each element in each of these compounds is the same. So if we represented the composition of these compounds through percent by mass rather than their actual chemical formula, we might mix them up. It's probably pretty bad to mix up formaldehyde and sugar. This is 40%, by the way. Okay. So it turns out that this CH2O is kind of a least common multiple of both formulas, right? Because 6 times CH2O kind of gives us C6H12O6. This multiplication is not exactly right? But you see what I mean. We can multiply this smaller formula by 6 to get the bigger formula. So we call this formula an empirical formula. An empirical formula is a formula that may not be reduced any more in any of its subscripts, right? So in other words, we can't reduce any of the numbers by a common factor anymore, right? So we could write down some formulas. It could be an empirical formula, CH3O, C2H7O2, C2H8O2, and N2O4 and NO2, right? Well, for N2O4, we could divide both numbers by 2, and we actually get this one. Here we can see 2 and 8 and 2 are all divisible by 2. So the empirical formula is going to be CH4O. CH3O, can't reduce that any further. C2H7O2 can't reduce that any further, right? So an empirical formula is just a formula that we're going to reduce into the smallest set of integers. And it turns out that that's going to give us the same percent by mass. Now, we were able to turn a chemical formula into a percent by mass. Is it possible to go from percent by mass to a chemical formula? The answer is yes, but only to an empirical formula. So we can do this, but the result's going to be an empirical formula. it's worth it discussing how we get percent by masses, right? We have instruments called a mass analyzer. This is a schematic of how they work. And they're most commonly used to combust, say, a hydrocarbon, right? So we put some hydrocarbon into this instrument, it burns the hydrocarbon, and the products are well known. We'll actually work with combustions when we first balance equations. The products are CO2 and H2O and maybe some other things, but we get different absorbers that are able to absorb specific products of this combustion, tell us the mass. There's some sort of integrated circuit or integrated chip built into the instrument that is able to do the calculation, and it will spit out a percent by mass. Right. So let's see how this works with this example of adipic acid. Adipic acid, right? So adipic acid what we know from naming acids, right, is that there's going to be an H that's out front, and then there's going to be an anion. In this case, it's going to be HCXHYOZ. But what we typically do when we're figuring out empirical formulas is we absorb all the hydrogens together. So let's just call this CXHYOZ, and we're going to try to figure out X, Y, and Z. Okay. The way we're going to do this is we're going to use the law of constant composition. We're going to assume we have 100 grams of our adipic acid. This is going to be our standard assumption when converting percent by masses into formulas, empirical formulas. We're going to assume we have 100 grams of the stuff. What this means is that the percent by mass of each element converts directly into grams of the element. Right? All right, so let's use the information on this slide as an example, right? We're going to write down the percent by mass. We're going to write it down directly as a mass of that element. So 49.3 grams of carbon. We're going to write down 6.9 grams of hydrogen. We're going to prepare ourselves for a calculation. And 43.8 grams of oxygen. And prepare for a calculation. Now, let's convert each of these elements to their moles using their molar masses. 1 mole of carbon, 12.01 grams. 1 mole of hydrogen is 1.008 grams of hydrogen. 1 mole of oxygen is 15.9994 grams of oxygen, right? And it turns out I made my lines a little bit too long, so let me fix that before I go on. All right, so what we're going to get now is moles of each of these elements. For carbon, we get 4.10 mole. For hydrogen, we get 6.3 moles. Paying attention to sig figs here. And for oxygen, we get 2.74 moles. So now what we're going to do is we're going to realize that we can write a chemical formula here. Remember, the subscripts in the chemical formula are the relative amounts in moles or number of each of the elements in the compound. And we have those numbers here, right? They're not quite in the way we want them though, but let's write them down. Carbon 4.10, hydrogen 6.3, oxygen 2.74. What we really want to do is we want to convert these into integers, right? And the way to do this is to divide by the smallest. And the smallest one is the 2.74. Carbon 4.10 divided by 2.74. hydrogen 6.3 divided by 2.74. Oxygen 2.74 divided by 2.74. This, of course, gives us a 1 subscript for the oxygen, carbon 1.5, hydrogen 1.3. Still not integers, but what we want to do now is we want to recognize decimal forms of fractions, right? 0.5 is the same as a half. 0.33 is the same as 1/3. 0.25 is the same as 1/4. 0.4 is the same as 1/5. You don't see this. No, I'm sorry, that's not right. It's 0.2, isn't it? 0.2 is the same as 1/5. We really don't see 1/5 too often, but we see these other three very commonly. So what I'm going to do is I'm going to write 1.5. This is the same as 1 1/2 or 3/2, right? 1.3 I'm going to recognize as 1.33 or 1 1/3 or 4/3 and so on. So let me rewrite this again. Carbon 3/2, hydrogen 4/3, oxygen 1. Now what we want to do is we want to get these into common fractions. Okay, so once we have these set up, let's go ahead and solve this. We get 4.1 moles of carbon. We get 6.84 moles of hydrogen. And we get 2.74 moles of oxygen. So what we're going to do now is we're going to put these into a formula. Remember, the subscripts in the chemical formula represent the relative number of moles or relative number of atoms of each of the elements in the compound. We have that ratio here. We have these relative amounts here. They're just not integers yet. Carbon 4.1, hydrogen 6.84, oxygen 2.74. In order to get these into the smallest, in order to get these into integer ratios, we're going to divide by the smallest number. In this case, it's the 2.74. Carbon 4.1 divided by 2.74. Hydrogen 6.84 divided by 2.74. And oxygen is going to be 1, right? 2.74 divided by 2.74. What this does is it gives us carbon 1.5, hydrogen 2.5, and oxygen 1. At this point, what we want to do, because we still don't have integers, right? We want integers in our chemical formula, but we still have decimals. We want to recognize decimal forms of fractions. 1/2 is the same as 0.5. 1/3 is the same as 0.33. 1/4 is the same as 0.25, and so on. These are the three most common occurrences. Once in a while, you'll see 0.2, which is the same as 1/5, but that's pretty rare. So for the 1.5 in carbon, we want to recognize this as 1.5, which is the same as 3/2. The 2.5 in hydrogen, we want to recognize as 2.5, which is the same as 5/2. So now we're going to rewrite this in this way: carbon 3/2, hydrogen 5/2, and we want to write the oxygen in the same denominator form, 2 out of 2. In this way, we can see the ratio more easily as carbon 3, hydrogen 5, O2. C3H5O2. This is going to be the empirical formula of adipic acid. Right? Now, what about the molecular formula? In order to know the molecular formula, we usually need some more information. The most common way to do this is use the gas laws and the boiling point. We're not quite there yet. We'll do this when we talk about gases. For now, usually we're just going to be given the molar mass. This slide says the molar mass is about 146 grams per mole. What we want to do is we want to find the empirical formula mass, right? This is going to equal the molar mass divided by some number, or in other words, do you remember what we did before? CH2O equals C6H12O6 multiplied by 6. So what we have here is the empirical formula. So in other words, we have this. We want this, so we want to find this number. The way we find this number is the empirical formula mass divided by the molar mass gives us this N number. And then we'll multiply all the subscripts in the empirical formula by this N. Okay, C3H5, C3H5O2. Let me find my notes here. The empirical formula mass is 3 times 12, 5 times 1, 2 times 16. Now you'll notice I'm using, whoops, covered this up here. You'll notice I'm using not very many significant figures for the mass, but this is going to be good enough to solve the problem for me. So 36 plus 5, which is 41, plus 32, which is 74, 73, right? All right, so the empirical formula mass, and I did this backwards, this should be the molar mass divided by the empirical formula mass, right? 146 divided by 73 equals 2. So we multiply all these subscripts by 2. C6H10O4 is going to be the molecular formula for adipic acid. And that's how you do it. Okay, let's talk now about chemical equations. This is section 3.6 in Zumdahl. It's kind of useful to understand the difference between chemical equation versus reaction. And scientists and chemists are pretty particular about language. Some would say anal retentive. But this is one of the times. Chemical reaction is actually something that happens in a reaction vessel on the bench top or or so on. That's something real. And a chemical equation is just the representation of this that you write down on paper. And the word equation is important because hopefully it makes you think of a mathematical equation. The equation, one of the ways is an equation is through mass balance. Right? Mass balance is the idea behind the equality in an equation. So if we look at a typical chemical equation like we have on the slide here, generically we could write this as reactants yield products. So the reaction arrow moving to the left means yields. Actually moves to the right. I'm reversed here because of the video. So generically, the things on the left are the reactants, the things on the right are the products, and the reaction moves forward left to right, and we use that to represent the arrow. But the arrow also can represent an equal sign. And in a balanced chemical equation, the way we conserve mass, the conservation of mass, is the mass of the reactants used must equal the mass of the products formed. Now, this used and formed is important because many times, as we'll see, we will have excess reactants. So we might start out with 100 grams of reactants and only get 75 grams of product, but that implies that 75 grams of reactants were not used. So the overall conservation of mass holds, but it just may be that some of our reactants were not used, right? And this is the idea of limiting reactants we'll talk about at the end of this chapter. So in chemistry or in chemical equations, the conservation of mass really is conservation of atoms. So the way we're going to conserve mass is through atoms. In other words, we balance atoms in a chemical equation. So if we look at our reaction over here on the left, C2H5OH plus O2 goes to CO2 plus H2O. This is what we would call an unbalanced reaction. Right? And then if we were to balance it, then we would have, let me rewrite this again, C2H5OH plus O2 goes to CO2 plus H2O. Now, if we put in coefficients, right, of 3 and 2 and 3, these are called the coefficients. There is an implied 1 in front of the C2H5OH ethanol. There's an implied 1, and these represent the molar ratios of all the species, right? So we say 1 to 3 to 2 to 3, and these are going to be the stoichiometric ratios, right? We call those the stoichiometric ratios. Now, one other thing that's important, and we don't want to forget, states are important. especially when we deal with thermodynamics, we're going to find states are important. So if I write the full balanced equation here, including states, I'm going to have C2H5OH. This happens to be a liquid at normal conditions, plus 3O2 gas goes to 2CO2 gas plus 3H2O gas. Now, I know water is normally a liquid. We think of water as being a liquid, but this happens to be a combustion, right? This is a combustion, and under combustion conditions, we produce water vapor. Okay. All right. Certain conditions may be represented over or under the reaction arrow. This is commonly used to express conditions, so it might be something like this. That's supposed to look like a symbolic flame, and it represents generic heating. You could put the temperature down. You could put the pressure along with the temperature, and so on. So very often you see conditions written on top of or under the arrow to tell a little bit more about what's happening. Okay. All right. Let's now talk about balancing. Balancing chemical equations, right? The first thing we want to do in a chemical equation, generally, at least at this level, right, we're going to have an unbalanced chemical equation. It's your goal, your chore to have to balance it. So that's what we're going to do. Now, there are some basic tips about balancing here that I want to point out. This says starting with the most complicated molecule, right? What we're generally going to do is we're going to start with the most complex molecule or species. I'm not going to call it a species if it's not necessarily a molecule. And we're going to finish with an elemental form. And in between, we're going to bounce back and forth between species, okay? Let me give you an example of a generic class of reactions. A hydrocarbon, HC, hydrocarbon combustion. Now, you're going to be expected to be able to balance a hydrocarbon combustion no matter what the specific hydrocarbon is, right? The basic form of a hydrocarbon combustion is you get a hydrocarbon plus oxygen reacts to form CO2 plus water. Now, the hydrocarbon is going to be something that looks like CXHYOZ. It might be an acid. It might be something even containing nitrogen and sulfur. If that's the case, then what we're going to do is form SO2 and NO2. So the general form of this is actually going to be pretty simple, because after doing a couple hydrocarbon combustions, you are going to find out that there's certain patterns. So to start out, what I'm going to do is I'm going to do a hydrocarbon combustion, C3H8 gas plus O2 goes to CO2 plus H2O, right? And let me be a little bit more careful here, right? Because I said we need the states. Gas goes to CO2 gas plus H2O gas. So here's the unbalanced reaction, skeleton reaction we want to balance. Now, the one thing we know here is, remember, we're going to do the most complicated molecule first. We're going to start with that. So we're going to start with the C3H8, and the oxygen is going to be last. All right, C3H8 gas. Notice that the carbon in the C3H8 only goes one place. It only goes to the CO2. So I'm able to take the 3 carbon atoms and put them directly to the 3 CO2, right? Next, I'm gonna kind of bounce back and forth, and let me do the water. Right now there's oxygen here, but I don't want to try to balance the oxygen. Remember, I want to do the oxygen on the reactant side last. I'm going to do that one last. So the next step would be, I'm assuming now the CO2 and the C3H8 are properly balanced with respect to each other. Now I want to move from the C3H8 to the H2O. Notice that the hydrogen in the H2O occurs in pairs. So if I have 8 hydrogen atoms in C3H8, I only need 4 waters, 4, right? So now, here's the order I've gone. I've gone from C3H8 to the CO2, I've gone to the H2O. Now what I'm gonna do is I'm gonna have to take both of these to balance the oxygen, right? So what I want to do now is I want to balance the oxygens. 3 CO2s equals 3 O2s. It's not exactly right? Because I'm pulling those out of the molecule. This is 6 oxygen atoms. 4 H2O gives me 4 oxygen atoms. The sum is 10 oxygen atoms. But look, the oxygen occurs in pairs. O2. So 10O, 10, it's a little bit confusing, right? Handwriting. 10 oxygen atoms is the same as 5 O2s in terms of atoms. So this allows me to balance the oxygen. Remember, I said I was going to do that last. C3H8 plus 5 O2 gas yields 3 CO2 gas plus 4 H2O gas. Right, so that's our balanced combustion reaction for propane. C3H8 happens to be propane. Now, it turns out that an odd number of carbons in the hydrocarbon is easier than an even number. Here's what I mean. Let's see how this works. What if I do a very similar hydrocarbon, C4H10? This is butane. The skeleton of this reaction is going to be the same. The hydrocarbon plus oxygen is going to give us CO2 plus H2O, right? So this is the basic form of a hydrocarbon reaction. Now what I'm going to do is I'm going to do the same path I did before. I'm going to take the 4 carbons and I'm going to give 4 CO2s. I'm going to take 10 hydrogen atoms, and that gives me 5 H2Os. Now let's count the oxygens. Remember, that's the last thing I have to do last. Count oxygen atoms. 4 CO2 gives us 8 oxygen atoms. 5 H2O gives us 5 oxygen atoms. Now there's 13 oxygens. Well, this doesn't give us an easy way to get pairs of oxygens, right? This has to go to some number of O2s, right? Here's our O2. It has to give us some number of O2s. Well, the good news is remember what these coefficients are. These coefficients you can think of them as being molecules, but it's better to think of them as being moles of molecules, right? So what I'm going to do is I'm going to say that 13 oxygens is the same as 13 halves O2. And you're like, how can I have a half of a molecule? But I don't have half of a molecule. This is 13 halves moles, which is the same as 13 halves times Avogadro's number, which is the same as 13 halves times 6.022 times 10 to the 23 molecules, right? Now, let's think about significant figures and precision here. The half is not ever going to give me half a molecule because it's beyond the limit of my precision, right? It's beyond the limit of my sig fig, 6022. And now I've got 20 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. If that last digit happens to be an odd number, I'd never know it because my limit of sig figs is way out here. This is out in the uncertainty. So I'm allowed to take fractions of these coefficients, okay? So what that means is my balanced chemical equation for CO2, oh, that's not CO2, right? For C4H10 plus 13 halves O2 goes to 4 CO2 plus 5 H2O. So this is technically okay. Fractions work in the sense that I just mentioned before, that these fractional coefficients really are okay, right? Because Avogadro's number is such a large number. However, the best practice is to eliminate fractions. These work, we can do stoichiometry, we can do all the calculations we need to do for limiting reactants and so on with fractional coefficients. But it turns out it's going to cause us problem when we talk about equilibria and also thermodynamics. There are standard ways to write reactions, and it turns out sometimes those stoichiometric coefficients can change things if we don't pick a standard way. So it's the best thing to do is to not use fractions at all. And I notice now I made a mistake up here, right? This wasn't a 4, this was an implied 1. So let me review. 1 C4H10 plus 13 halves O2 is 4 CO2 and 5 H2O. Now, if I want to get rid of the fraction, all I have to do is multiply everything by a factor of 2. If I multiply every coefficient by the same factor, it doesn't change the balancing at all. So what this gives us for our best answer is 2C4H10 plus 13O2 yields 8CO2 gas plus 10H2O gas. So what this means is if you get, or if you need to balance an even hydrocarbon, an even number of carbons, double the amount. 2CXHYOZ, right? Now, I know I didn't balance a hydrocarbon with an oxygen there, but that oxygen, if you happen to get an oxygen in the hydrocarbon, that's going to end up combining with the oxygen on the left to give us the water on the right. An example of this is the ethanol that we did before. Remember, we already did this one. This is actually going to turn out to be 7/2 O2. Goes to 2 CO2 plus 3 H2O. And then, of course, we're going to get rid of the fraction. So here we have an even numbered hydrocarbon. Even if we have oxygen in there, we're going to want to double it. 2C2H5OH liquid plus 7O2 gas goes to 4 CO2 gas plus 6 H2O gas. You should check this to make sure you agree with my balancing. All right. Let's look at the slide, because which of the following correctly balances the chemical equation, this one written in blue? And there can be more than one answer, but there's really only one best answer, right? All right, so we have to balance this chemical equation. First of all, CaO plus C goes to CaC2 plus CO2. Well, we're going to balance this carbon last, right? I see there's 2 carbons there. There's a calcium here, and it looks like the important thing is going to be the 2 oxygens and the 1 oxygen. So let's try this. 2CaO plus C goes to CaC2 plus CO2. That balances the oxygens. I have 2 calciums on the left. That means I need 2 calciums on the right. You see now it was a good idea to balance that carbon last, because I have 4 carbons here, 2 times 2, and 1 carbon here. So this is going to be 5 carbons. Okay, so 2 calcium oxides plus 5 carbons gives us 2 calcium carbides plus 1 CO2. And we can see that that is the balanced equation, but there are other representations, right? As long as the coefficients are multiplied or divided by a common factor, it's okay. So we can see that number 3 is also okay. Everything's been divided by 2. We can see that number 4 is okay. Everything's multiplied by 2, right? So even though the third one is the best one, that's probably the one we want to use. 2, 3, and 4 are all okay. Okay. Let's make sure we understand the concept here, right? Let's talk about some things about a balanced chemical equation. Which of these are true? There could be more than one true. The number of molecules is conserved. Well, remember we have conservation of mass, and we translate that into conservation of atoms. The number of molecules may not be conserved. In fact, if we look up here in this one we just did, and we count molecules, we have 2 and 5, we have 7 on this side, we have 2 and 1 on this side. In terms of molecules, they're not conserved. So statement 1 is not necessarily true. It could be true, but it's not always true. The coefficients tell you how much of each substance you have. Yeah, that's true in a number amount. That's not worded the best way, but I guess that's true. Let's circle it. Atoms are neither created nor destroyed. That is certainly true. We use conservation of atoms, right, to do conservation of mass. The coefficients indicate the mass ratios. Well, these are not the mass ratios, right? They're the number ratios, the mole ratios. The sum of the coefficients on the reactant side equals the sum of the coefficients. That's really saying the same thing as number 1, right? The sum of the coefficients is really the number of molecules, so that's not necessarily true. So I think only 2. That's funny. That is not true. The coefficients indicate the mass ratios. That is not true. I have to fix that slide. Okay, remember, once we have a chemical formula down, a compound, a molecule, we don't change the identity of that compound to balance the chemical equation. So in all of these examples, I never changed the chemical formula of anything. The only thing I can do is change the coefficients, right? And this can make it hard sometimes, but that's the way we have to do it. Okay. Let me give you one more hint. Often, ions are balanced together. In other words, what we want to do is we want to balance polyatomic ions very often instead of trying to balance the atoms individually within the polyatomic ions. Let me give you an example. Magnesium nitrate. This might be aqueous solution plus aqueous sulfuric acid goes to HNO3 and magnesium sulfate. What I want to do here is I don't want to try to balance sulfurs and oxygens and so on individually. I want to look for things like nitrates, right? Nitrates exist here and here, right? And I also have sulfates here and here. So what I'm going to try to do is balance those together, right? And here I see that there's 2 nitrates in magnesium nitrate. So I'm going to make that a 2, right? And this 2 now is going to match the 2 hydrogens in hydrogen sulfate. That's really not hydrogen sulfate, right? It's sulfuric acid. It looks like everything else is balanced though. So the final coefficients are going to be 1 magnesium nitrate plus 1 sulfuric acid yields 2 nitric acids and 1 magnesium sulfate. Okay, let's do another practice problem. This deals with reaction in the space shuttle engine. The space shuttle is not used anymore, but it was for a long time. And it was an interesting reaction, right? Aluminum, it's actually powdered aluminum, is combined with ammonium perchlorate. And this produces aluminum oxide plus aluminum chloride plus NO gas plus water. Okay. This reaction is pretty complicated, and the difficulty here is we have aluminum in 2 places on the product side, but we only have it in 1 place on the reactant side. So what are we going to want to do here? We're going to want to balance the aluminum last. We're going to want to balance the most complicated species first. Which one is that? I don't know. Maybe we'll start with this. That looks pretty complicated. All right. Well, this might be a little hard to see, a little difficult to see, right? Here we have chlorines and here we have chlorines. We have oxygens in a lot of different places. We have nitrogen in 1 place, but it already looks balanced there. 1 nitrogen, 1 nitrogen, and we have hydrogen going to water. Well, it looks to me like maybe the chlorine is going to be the easiest one to balance. And in aluminum chloride, it occurs in triples, right? AlCl3. So you may be tempted to make the ammonium perchlorate a 3. However, I'm going to tell you that odd coefficients are not too common, and if you double a possible odd coefficient to an even coefficient, the worst case scenario at the end, you're going to have to divide by 2, right? Which is pretty easy to do. So the first thing I'm going to do, I'm going to leave off the states because I'm going to do this step by step, is I'm going to make this a 6. And then I'm going to make this a 2AlCl3, right? Al2O3, NO, and H2O. So I think this chlorine is balanced and this chlorine is balanced. Now we can start taking that ammonium perchlorate to other places, right? The first place might be to balance the nitrogen, 6 nitrogens, right? I didn't mean to make that green. I'll go back to black. 6 nitrogens. Oxygens are occurring in a lot of places, right? But as a reactant, it only occurs in the ammonium perchlorate. So I'm going to find out the total number of oxygens. 6 times 4 is 24 oxygens, right? And oxygen occurs in the aluminum oxide and water. So oxygen, I don't think we're ready for oxygen yet, but notice that we have hydrogen only in one place as a reactant, one place as a product. So we can see that we have 24 hydrogens also. In water, hydrogen occurs in pairs, so this is going to be 12. Now I think we're ready because the only thing we don't have balanced is the aluminum oxide and the aluminum, right? The leftover oxygens are going to go towards the aluminum oxide. So let's count out the oxygens. 24, right? I have 12 oxygens here. I have 6 oxygens here. That means I need 6 oxygens here. Now this is getting a little messy, right? Aluminum plus 6 ammonium perchlorates goes to Al2O3, don't have that balanced yet, plus 2AlCl3, we have that balanced, 6NO, we have that balanced, and 12H2O, we have that balanced. So remember what we did is did the 6 here, we have to deal with the 6, and now we can count the aluminums, and we'll be all done. We have 12 aluminums here, we have 2 aluminums here, so the total is 14 aluminums. Is that right? That doesn't seem right to me. 12 aluminums. Oh, you know why? This should not be a 6. There should be 6 total oxygens, but that means 2 aluminums. So this is 4 aluminums here with the 2 aluminums, 6 aluminums total. So we have a 6 there. All right, let's see what we get. 6Al plus 6NH4ClO4 goes to 2Al2O3 plus 2AlCl3 plus 6NO plus 12H2O. Again, I'm leaving off the states just to make it a little bit easier. Notice all these coefficients are divisible by 2. So this is that worst case scenario I mentioned before, but this isn't too hard to make this kind of a final balancing. 3 aluminum, we just divide everything by 2, plus 3 NH4ClO4, going to Al2O3 plus AlCl3 plus 3NO plus 6H2O. So that's our final balanced reaction for this. That was kind of complicated, and you will run into some of these complicated reactions to balance. The good news is the most complicated equations to balance are oxidation reduction reactions. But the good news is is that we have a whole nother systematic method of balancing oxidation reduction reactions that we will learn in chapter 4. Okay, now we're ready to move on and talk about stoichiometry. Stoichiometry is what most people would consider to be real chemistry. We're going to get into working with chemical equations and figuring out how much stuff you can get from some other stuff and how it depends on this stuff and what happens if you change that stuff and so on. I have to apologize a little bit. There's going to be some rumbling noises in the background. My puppy is chewing on her favorite toy. Okay, so stoichiometry, technically, it is the number. Now remember, what that typically means is mole to mole, right? We're going to use moles for numbers. It's the number relationship between all the reactants and products in a balanced chemical equation. And we commonly just say species to refer to all the reactants and products. Now, it has to be balanced, right? Because if it's not balanced, then we can't have these relationships and we don't know what they are. Okay, so the problem is stoichiometry deals with the number relationship between the species, but typically we have the mass. We have masses of things, right? We just spent a lot of time talking about counting by weighing. That's how we count things, is by weighing them. So we are going to have to typically always do a conversion between mass and moles, and this is going to involve the molar mass, right? Okay, so let's look at the steps that we're going to have to do here. What I like to do is I like to think about this as two levels. At the chemical equation level, we're going to use moles, number, but we're typically going to be giving masses of things. Later on, we're going to work with solutions and figure out how to deal with those kind of things. But it's really not much different. We're going to have masses. We're going to have to move up to the chemical equation level of moles using the molar mass. We can use stoichiometry to go across the equation and come back down. We're going to balance the equation. We always balance the equation. Never assume the equation is balanced. Although I have to say, if you look at a chemical equation and it already has coefficients, you can safely assume it's balanced. I will never give you a chemical equation with a bunch of coefficients and try to trick you by saying, oh, you didn't balance it, these aren't right. If all the coefficients are ones or implied ones, you should check it. And it's probably not balanced. We're going to convert the mass of the reactant or product to moles. We're going to use balanced equation to set up mole ratios. We're going to use the mole ratios to calculate the number of moles of the reactant or product. Now we can go back and forth. We don't have to go from reactant to product. We can work backwards from product to reactant. This is very powerful. And we'll convert from moles back to grams using the molar mass. So here's kind of a schematic of how this works. I'm going to do a different schematic with this example. So let's write down this example. This is an example of a synthesis. You would call this a synthesis reaction because we're making one product from more than one reactant. Okay, this has the coefficients already, so we're going to assume that this is balanced. Now, in order to use stoichiometry, we need to work up here on this high level next to the chemical equation, right? And we will have the moles going across the reaction arrow back and forth. In this particular problem, it says we're going to take 6.25 grams of phosphorus, and we want to know how many grams of oxygen it will combine with. This is a stoichiometry problem, even though we're not working with the amount of product. We're going to figure out how much oxygen is required to exactly use up all the phosphorus. This is just like a recipe. A recipe is stoichiometric. In order for your recipe to turn out properly, you need to follow the directions, which are kind of like a chemical reaction. It might say a tablespoon of honey is going to go with 3 tablespoons of soy sauce, and there's some other things, right? But at least that relationship between those two things is going to be 3 to 1. All right, so what we're going to do here is we are going to convert to moles of phosphorus using molar mass. That's going to give us the moles of phosphorus. We're going to go across to moles of O2 using stoichiometry. And then we're going to use the molar mass of O2 to find the grams of oxygen. So that's how it's going to work. One thing you're going to have to do very often, most of the time, before you get started, is to figure out the molar masses of your species. Phosphorus, the molar mass of a single phosphorus atom is 30.97. So you should find the molar mass of P4 is 123.9 grams. I worked this out beforehand. For O2, the molar mass is going to be 32.0 grams per mole. And I'm using 1 decimal place for this. You can use 2. Remember I said using 2 decimal places is pretty common for chemical calculations. So how do we do this? Each one of these arrows I drew, except for this one, I'm going to erase this arrow now so it's not confusing. Each one of these arrows is going to be another step in our mathematical calculation and our dimensional analysis. So let me set up my dimensional analysis, and the first part of this is going to be the 6.25 grams of P4. Remember, we want to label what we have. The next thing we're going to do is we're going to convert from grams to moles. So I'm going to put grams down here and moles down here. 123.9 grams is 1 mole of P4. Now I have a habit in the next step of doing something special for the stoichiometry, because now if I stopped at this point, I would have the moles of P4. I can now use the chemical equation and stoichiometry to find the moles of oxygen. And the way I do that in my diagram is I always box this. Okay, there's a couple reasons why I do this. One is to point out the very important step of using stoichiometry. And later on, I'm going to fudge this a little bit, okay? And you'll see what I mean in a lecture or two. And I want people to see, I want you to see where the stoichiometry is. The stoichiometry is very important. So what we're going to do now is we're going to convert from P4 to O2. And that relationship is the 5. Here's the 5. 5 moles of oxygen for every 1 mole of P4. That's the very important stoichiometric conversion. The last step is going to be this step here, converting from moles of oxygen to grams of oxygen. .0 grams of oxygen is 1 mole. And when we do all this math, what we find is this is 8.07 grams of O2. And what I'm going to also do is I'm going to So be a little bit more specific about this. 8.07 grams of O2 required to use the 6.25 grams of P4. That's really what it is. Okay, so that's our answer. This is an example of a simple stoichiometric calculation, like a recipe. This is the exact amount that we need to use this up, 8.07. Good, we got the right answer. All right, so before we get into figuring out specifically the amount of product, let's do a comparison type problem. Now, you've probably heard me say at least once, and you'll hear me say it a few more times, that we, and when I say we, I mean me and the other professors we hang out with, that I hang out with, we really like this book because the problems are real world problems. They're not just one-step problems. They're more like problems that you would have to solve in a real world situation. So we have this situation that we're going to get into in this problem now. Methane reacts with the oxygen in the air to produce carbon dioxide and water. Okay, so this is giving us an equation. Let's for now leave off the states. That's kind of cheating, right? I've said that the states are very important, but we're going to ignore it for this problem just to save a little bit of time. All right, so that's the equation. It's not balanced yet, but that's the equation. Methane reacts with the oxygen in the air to produce carbon dioxide and water. Ammonia, right, another common household chemical, reacts with the oxygen in the air to produce nitrogen monoxide, NO, and water. So these are two reactions. Step one, write balanced equations for each of these reactions. So you can pause the video now if you want to, because I'm going to just give the answer. And if you work on this a little bit, it's pretty simple. 2 oxygens and 2 waters, but the other coefficients are 1. The ammonia reaction is a little bit more difficult to balance. This probably took you a little bit longer. 4, 5, 4, and 6. All right. So here's the problem. What mass of ammonia would produce the same amount of water as 1 gram of methane reacting with excess oxygen? Okay, while we think about that for a minute, let's start with the last part. Excess oxygen. What does this mean? This means that probably we're doing this reaction in air. In air, we have an infinite amount of oxygen as far as our reactants, our other reactants are concerned. We are not going to run out of oxygen. So what we're going to do is we're not going to worry about the amount of oxygen. We're going to assume that we have plenty of oxygen to use up our other reactants. So that's kind of nice. Excess oxygen, there's enough O2 to use all of the CH4 and NH3. That's what that's going to mean. All right, now let's think of the other part of the problem, right? The hard part of the problem. This says, what mass of ammonia would produce the same amount of water as 1 gram of methane? Let's write this down. We're going to have 1 gram of methane. What mass of ammonia would produce the same amount of water as 1 gram of methane reacting with excess oxygen? So what we're going to do here is we're going to take the 1 gram of methane. We're going to calculate the amount of water needed. We're going to equate that to the amount of water, and I said water needed. I should have said water produced. We're going to equate that to the amount of water produced in the second reaction, and then we're going to work backwards to figure out how much ammonia would have produced that much water. Now, I don't want these differing coefficients to confuse you. The coefficients are just per the reaction, and that's separate from the conditions that we have or the amounts that we have, right? So again, each one of these arrows is going to be a step in my dimensional analysis problem. All right, so I'm going to do this all in one step, but I'm going to show you where we could stop. Okay. In other words, we could stop at this point here, right? And I'm going to use an I for an interim answer. We could figure out the interim answer there. We're going to start with what we have, 1 gram of methane. Remember, the first thing we're going to do is convert it to moles, grams of CH4, moles of CH4. The molar mass of methane is 12 plus 4, 16. So I'm going to say 16.0, 1 mole of CH4. Now the stoichiometry, right? The stoichiometry is 2 moles of water for every 1 mole of CH4. Remember that 1 is implied. All right. Now, if you do this in 2 steps, very often students will calculate the mass of water by using the molar mass 18, but you don't have to do this, right? You don't have to do this, because if you stopped here, the next step would be this other arrow, the third arrow. Remember, this is the first arrow. 1, 1. This is the second arrow. So let's call this I, since I already labeled it that way. And then we have another arrow. So it turns out we don't need to do this, right? The next step, we could tack on this third arrow, which is the stoichiometry of the second reaction, 4 moles NH3 for every 6 moles H2O. And then the final step would be the molar mass of ammonia, converting the moles of ammonia to grams of ammonia. 17.0 grams of ammonia is 1 mole NH3. All right, so we can do the calculation in the first step. The calculation in the first step is just 1 divided by 16 times 2 over 2. For some reason, I don't have this done. This is 0.0 Now, if you were to tack on the molar mass of water to find the mass of water, you could do that. And what you would find is 2.25 grams. I'm putting this down just in case you did that. The problem with this now, though, is if we move on to the second part, actually the third arrow, we have to convert back from grams of water to moles of water to be able to use this stoichiometry, right? So that 2.25 grams of water is kind of a wasted calculation if you do it all in one step. You might need to think about that for a minute, but that's how it goes. All right, so if I take this 0.625 moles of water, or just tack this the second line onto the first line, right? I'm going to multiply this by 4 over 6. And then I'm going to multiply it by 17 grams per mole. And what I'm going to get is 1.4 grams of ammonia. In other words, 1.4 grams of NH3 produces the same amount of water as 1.0 gram of CH4. This kind of calculation might be useful if you apply it to something like different fuels. How many grams of CO2 would 1 gram of methane produce versus 1 gram of hydrogen, right? That might be kind of an interesting calculation to calculate the amount of greenhouse gas you would produce from different fuels. So this kind of comparison problem is kind of common in chemistry. So these slides here will just go about how to do it, that kind of calculation. Now we're going to move on to more complicated and more general kinds of chemical stoichiometry reactions. I don't want you to worry though, because at the end of the lecture video, at the end of the lecture part of this video, I will do a few problems. That makes the lecture video longer, and you can ignore that part if you want to, but if you need the extra help, at least you have that and you can continue to watch. It's actually from a different session, but it's still me. Okay, next, limiting reactants. If you think about it, figuring out the exact stoichiometric amount of a reactant and product to make sure that they all react 100%, nothing is left over, that's kind of a pain, right? It's a very hard thing to do. Typically what we do in a chemical reaction is we have something that's like the fuel, and we have something else that's like oxygen that's excess, right? So we didn't say that in the problem we just did, but when we have one species in excess, the other species is the limiting reactant. The limiting reactant is what all the other amounts are based upon. All the other amounts of product and other reactants that we use up are based upon the limiting reactant. So in general, if we have two reactants, one's going to be in excess and one's going to be the limiting reactant. And if you think about it, the more expensive or difficult to get reactant is going to be the limiting reactant, and the one that's more inexpensive or easy to use is going to be the species in excess. The other assumption we make is that the reaction is 100% complete, and we'll treat that after limiting reactants. So if that's kind of in your mind and back of your mind, just wait a few minutes and we'll talk about that. And of course, to save time, I usually just write the letters excess to represent excess. All right, so let's start with a relatively simple problem. Well, actually, before we do the simple problem, let's look at a few of the slides so we can catch up. So if we look at the Haber reaction is nitrogen plus hydrogen forming ammonia. By the end of this semester, you're going to be sick of this reaction because we can use this reaction for every single concept in a freshman chemistry class. It's a very, very useful reaction for many reasons. Okay, so the Haber reaction is 1 mole of nitrogen for 3 moles of hydrogen, giving us 2 moles of NH3. Here's a cartoon that shows this, and we would call this a stoichiometric reaction. In other words, the reactants and products, therefore, but the reactants are in their stoichiometric proportions. That's stoichiometric. So the idea behind limiting reactants is this is actually not too common. It's better to kind of get in the neighborhood of stoichiometric, or maybe we don't even want to be that careful. But it's not too hard to calculate what the limiting reactant is and go with that. So here's an example where we have these circles around the stoichiometric amounts, 3 hydrogens to 1 nitrogen, but we see we have some nitrogen left over. So what that means is that each of these little circular enclosures here that we've drawn will give us 2 NH3s, but we have some nitrogen left over. So species in excess, they will be left over after the reaction is complete. Okay. Limiting reactant is the reactant runs out first. So I'm not quite sure what this problem is working on, but I'm going to do a different problem that I have prepared. Okay, so what if we have the reaction of aluminum with bromine? I have this balanced. I'm assuming that by now that you're very good at balancing, so we don't have to work on that anymore. All right, so in this problem, we're going to be given 6.0 grams of aluminum and 15 grams of bromine, and we want to know how much product we're going to get. Now, remember, the way I kind of drew this down is what we're going to do is we're going to calculate the moles of each of these reactants using the molar mass. And after we can do that, we can somehow go across to figure out how much product we're going to get in moles. And then again, we go down using the molar mass to find out the mass of the product. But we have to put a little bit of thought behind this, right? Because we need to figure out some way to which one's the limiting reactant. And then once we know what the limiting reactant is, we're going to forget about the other one and just focus on the limiting reactant to figure out the amount of product. There's 2 ways we can do this. Okay, the first way is, for some people, it's simpler. What we're going to do is we're going to take the amount of each reactant in turn and determine the amount of product we would get as if that was the limiting reactant and the other species is the excess. So we do each of these and then we pick the smaller, right? Does that make sense? Because whatever the limiting reactant is going to give us the smaller amount of product. Let me give you a quick example, right? Let's say that I'm going to have a barbecue this weekend and I'm going to make some hamburgers. I like hamburgers. So I have buns. Let's say I have brioche buns. So they're pretty much identical top and bottom, and they all got mixed up. So I need 2 buns for every hamburger. And what I'm going to do is I'm going to make a bunch of hamburgers and hope my buns work out. So if I have 15 buns and I have 8 hamburgers that I've cooked, how many hamburgers complete am I going to have for people? Well, 1 hamburger requires 2 buns, right? Can you think, okay, 8 hamburgers, I need 2 buns. So this, I could possibly get 16 complete hamburgers just based upon the patties, right? Whether they're meat patties or plant-based patties, right? Same thing. Okay, but if I only have 15 buns, I have to go the other way, right? I need 2 buns for every complete hamburger. So I need to divide by 2. This gives me 7.5 hamburgers, but of course, I'm not going to make half a hamburger. I want a whole hamburger. I don't want to disappoint people. This is going to give me, or this is going to require 7 patties, right? So I could get 16 complete hamburgers based upon how many hamburgers I made, but I could only get 7 complete hamburgers based upon the buns. So the buns are the limiting reactant, and the amount of product, the amount of hamburgers I'm going to do is 7. We do this kind of thing all the time. Usually making food, right? Because food is very good, and everybody enjoys food. But that's the basic way that we do limiting reactant calculations day to day. So maybe that helps you understand. So let's look at this first way, which sometimes I call brute force, because it turns out you're doing a little bit more calculation than you have to. But as I said, for a lot of people, it's more clear. So the first thing we're going to do is we're going to start with 6.0 grams of aluminum. First thing I'm going to do is convert to moles. 1 mole of aluminum is 26.98 grams. I looked at my periodic table. Now the stoichiometry, if we look at our balanced chemical equation, 2 moles of product, AlBr3, from 1 mole of aluminum. From 2 moles of aluminum. And then what we're going to do is multiply by the molar mass of the product. Let me write that up here. I should have written that up here to begin with. It's 266.7 grams per mole. And usually I'm going to write the formula of the product in there, but I don't have enough room, so I'm not going to cram it in there. Let me say one thing about this stoichiometry part that I always put a box around. This is 2 moles to 2 moles, and you may be tempted to write 1 mole to 1 mole. It's the same thing, right? 1 mole to 1 mole is the same as 2 to 2. But I don't ever want you to do that, because if you come back later and look at that 1 to 1, you'll look at your balanced chemical equation and say, there's no coefficients of 1 in this balanced chemical equation. I must have made a mistake. And it's a mistake that's not going to affect your overall calculation, right? Because 2 to 2 is the same as 1 to 1. But we always want to make sure to use the coefficients in front of the balanced chemical equations, because that's exactly where they come from, and that relates us back to the balanced chemical equation. So I don't ever want you to try to reduce those. Okay, so let's write down the result. The result here is 59.3 grams of AlBr3. Now, there's a condition for this though. This is the amount of product that will be formed if the aluminum is the limiting reactant. We haven't made that decision yet, because we have to do the other reactant. We have to calculate how much product we get from the other reactant. This is assuming, of course, I should have left a little bit more room. Br2 is the excess. That's really what we're saying, right? Br2 is the excess, aluminum is the limiting reactant, but we haven't made this decision yet. All right, so now let's do the other one, the other reactant, which is the bromine. One mole Br2, 159.8 grams per mole. The stoichiometry is 2Al2Br3 for 3Br2. And again, the molar mass of the product, 266.7 grams, 1 mole. Okay. Now you may notice something I did here. Some of you might be saying, where's the moles? Where's the moles? I warned you I was going to do this, right? I warned you a little while ago that I was going to do something that might confuse you, but the box helps me remember what I'm doing. I just wrote the number amount. I didn't write moles in there, but a mole to mole ratio is exactly the same as a number to number ratio. So very often, both to save time and just to get this point across, I will leave out the moles from this. But since I have a box around it, you know it's stoichiometry, right? Think about that. A mole to mole relationship is a number relationship, so I don't have to put the mole unit in there. Hopefully that's not confusing. All right, so what does this give us? This gives us 16.7 grams of AlBr3. And again, this is if the bromine is the limiting reactant and the aluminum is the excess. So what we want to do is we want to compare this amount to this amount, which is smaller. The second amount we calculated is smaller. So what that means is that we forget about the first one we did, right? That turns out not to be true. Bromine is the limiting reactant because it gives a smaller amount. Aluminum is the excess. Now, what does this mean? It means that we're done with this problem. We know how much product we have formed. It's important to realize the answer is one or the other, not both. Sometimes students get very good at this, but then at the end, especially maybe with all the pressure and nervousness of a test, they end up adding these two amounts together. It's one or the other, only one or the other. So make sure you realize that when you do this method, it's just one or the other. All right. The other method. Some people think this method is quicker, feels quicker, and it's called a direct comparison. What we're going to do is we're going to start with one reactant or the other, and we're going to determine how much of the other reactant is required to use up all of our first reactant. That tells us what the limiting reactant is. And then we can use that limiting reactant to figure out the amount of product. Okay, let's see how this works. You can pick one or the other. Doesn't matter which one you pick. What I'm going to do is I'm going to pick the aluminum. So I'm going to calculate how much bromine is required to use all, and the all is the 6.0 grams of aluminum. This is going to give us a mass of bromine. We compare this with what we have. If that bromine is more than we have, then the aluminum is the limiting reactant. If that, is that right? No, if that bromine that we calculate is more than we have, then the bromine is limiting. If that amount of bromine we calculate is less than we have, then we've got plenty of bromine available and the aluminum is the limiting reactant. Don't worry, I'll say this again. Let's do the calculation. 6.0 grams of aluminum. 1 mole of aluminum, 26.98 grams of aluminum. The stoichiometry is 3 moles of bromine for every 2 moles of aluminum. And now we're going to multiply by the molar mass of bromine, molecular bromine, 159.8 grams, 1 mole Br2. This gives us 53.3 grams of bromine, Br2, required to use all the aluminum. So let's go up here and see how much we have. We have only 15 grams. We only have 15 grams. Right? 15 is less than the amount that we need. So the bromine is going to run out first, and that's limiting reactant. This requires a second step, right? So the second step is to use the provided amount or the given amount Well, this may seem like we have to go back a little bit, and it is true, we have to go back a little bit, right? We have to start with the 15 grams of bromine, and some people prefer the other method because you get the answer, you get two answers, but one of them is the right answer, and you can stop at that point. So it just, for some people, that feels a little bit better. Right, there's the conversion to moles. Stoichiometry, 3 Al2 Br3 for 3, is that right? Let me check the stoichiometry to make sure. 3 to 2. So I have to fix this. It should be a 2. And then again, the amount of product, the molar mass of the product, 266.7 grams for 1 mole. This gives us, unsurprisingly, 16.7 grams of Al2 Br3 formed. This is the same answer that we got in our brute force. Remember, I call this the brute force method, but we should get the same answer. The correct answer should be independent of the way we find the answer. Right? So that's how you do a limiting reactant problem. What if you had 3 reactants? If you have 3 reactants, then you either have to do a three-way brute force, or 2 direct comparisons. And you can find, I think there's a problem or two in the book that does that. Next, and finally in this chapter, we have percent yield. If you think about it, it's pretty rare in life and chemistry when you're doing experiments that you get 100% of what you expect. So if we go back to the problem we just did, it would be pretty unusual if you did this experiment in the lab, 6 grams of aluminum and 15 grams of bromine, and got 16 or even 15 grams of aluminum bromide. That would be pretty uncommon. It turns out that Mother Nature just rarely gives us 100% yield. Actually, if we do better than 50% yield, we feel pretty good about it. So we need to be able to calculate the percent yield to have an idea of how quantitative our reactions are. What does that mean? Quantitative means 100% yield or nearly so, 99%. There's a lot of reactions that we do in freshman chemistry lab that are quantitative. These are useful so we don't have to do percent yields. Some reactions just go to completion very strongly, but most reactions give less than 100%. So percent yield needs to be calculated. Okay. Well, what is percent yield? Percent yield is defined as your actual yield divided by the theoretical times 100. Sometimes students have trouble remembering which is which, but the way you can think about this is the actual is the lab amount, the theoretical is the paper amount from a calculation. So the theoretical yield is just something you calculate. Okay, so let's do a typical problem. And I want to do a problem that's not a straightforward problem, like you get this much stuff and calculate the percent yield. I'm going to give you how much stuff you get and the percent yield, and we have to go back and figure out how much reactant we started with. All right. Let me catch up here. I think this might be on the slide. All right. So here's the reaction. P4 plus 6F2 goes to 4PF3. Right, this is all balanced for us, so we don't have to worry about that. What mass of P4 is needed to produce 85 grams? So the idea here is we want 85 grams of this product, but we only get 64.9% yield. So we might write that in the reaction arrow. So what we're going to do is we're going to work backwards to figure out the amount of P4. This is grams, but we have to take this percent yield into account. All right, so let's start by looking at the percent yield. 64.9% yield. What does this really mean? This means 64.9 grams of PF3 actual divided by 100 grams theoretical or paper times 100, right? But let's not use that 100 because the 100 is to turn it into a percent. And in a similar way that we did for isotope problems, the fractional amount is actually what we're going to use in a calculation. All right, so let's see how this works. 85 grams of PF3. This is the actual amount, right? This is the actual amount that comes out of our reaction. So if you think about it, if our percent yield is less than 100%, that means we're going to have to use more reactant than we might otherwise expect to get the amount of product that we need, right? So what we're going to do is we're going to arrange this fraction of 64 and 100 so that it's greater than 1. But we really, that's kind of the logical way to think about this, but we can also use our units, right? Because we want to get rid of the actual, so we can put the 100 grams of theoretical on the top, 64.9 grams actual on the bottom. So that's like our fudge factor to figure out how much we're going to get. Okay, now we can continue this and we can multiply by the molar mass of PF3 to convert it to moles. 1 mole PF3. I have to continue this on more than one line. 87.9 grams PF3, right? Our stoichiometry is going to be 1 mole P4 for every 4 moles PF3. Let's make sure that we are okay with that. We see that up here. And finally, we're going to multiply. Finally, we're going to multiply by the molar mass of P4. 123.9 grams is 1 mole P4. All right, so when we multiply this all out, The actual is going to cancel. The grams of PF3 is going to cancel with that. The moles of PF3 is going to cancel with there, and I'm going to end up with grams of P4. All right, when we do all this math, we should find that we have 46.1 grams of PF4, PF3 required to form 85.0 grams of our PF3. So that's one way to do a percent yield problem. This is a little bit kind of a step up from a straightaway percent yield problem. But as I've said, these problems in Zumdahl are a little bit more real life. This is actually a more usual kind of thing that you might want to know before you get into it, right? Very often you know how much product you want, and you're not going to get 100% yield. So you have to scale up everything, and it's convenient. If you know the percent yield, you can work backwards and figure out the amount of product you're going to get. All right, so after that finishes chapter 3. So as you're working on these problems, you can go ahead and look at the next part of the video, which is doing a few practice problems to help you gain some experience with this. I will see you in chapter 4.